Okay, time for one more recording for the chapter 5 topics. We need to discuss more about further types of hybridization that are used to create covalent molecules and talk about the kinds of orbitals that are used to make bonds in molecules and polyatomic ions that give us both sigma and pi bonds, and then recognize the components that are present in sigma and pi bonds. The previous discussions described sp3 hybrid orbitals. Now we need to look at some other types. There is another way of putting together atomic orbitals to make hybrids that explain the geometries that are observed, and that would be when you have an s orbital of such as like the 2s orbital hybridizing with two of the p orbitals, such as shown here, and you put them all together in a hybrid fashion, and we get what's called an sp2 hybrid set of orbitals. And these orbitals are going to lie in a plane at angles of 120 degrees, which should sound familiar from our VSEPR discussions. The sp2 orbital has a large lobe and a small lobe. We primarily look at the larger lobe of them. And these 120 degree angles between these three hybrid orbitals of the sp2 type are going to be all in a flat plane, but that leaves behind one other p orbital that was not used from that atomic orbitals on the original diagram. And so there is an unused p orbital that can be participating in different bonding subsequent to making the hybrids. So the green ones are the hybrid orbitals showing only their larger lobe, not the small one. Another diagram representing the hybrid orbitals is shown here, where you take one s orbital and two p orbitals. In this case, they're both from the second shell, hybridizing to make three equivalent new sp2 orbitals. Remembering that when we did sp3, same thing applied. You hybridize a number of individual atomic orbitals and create equivalent new hybrid orbitals. So the same thing is true here. There will be three sp2 orbitals, but they each have a slightly different orientation. But again, they're all going to end up at being 120 degree angles apart. So what you end up with is trigonal planar geometry and the 120 degree angles. An example of a molecule that has this is boron trifluoride. Now boron is an oddball because it doesn't make an octet, but here's what it would do if you make that compound of boron and three fluorines. And one way of representing this compound is to use an electron density map, electron density diagram that shows that the negative character of the fluorines is equally distributed on all three sides on all of the fluorine atoms because of the equivalent bonding to each of the fluorine atoms. So what happens? Let's keep looking at this a little bit more. Apologize for the scratchy throat, folks. So if you have a carbon atom that has hybridized sp2 orbitals that can be aligned with another carbon atom with sp2 orbitals that are facing it, then you can imagine where the carbons could be bonded to one another with those two sp2 orbitals overlapping in a sigma bond when they're head-on, as it were. So these two combine. In between the two spaces, you have now a shared pair of electrons, and being in the axis of the bond, or the direct line between the two atoms, we call that a sigma bond. So that one sigma bond can help to hold them together, the first bond between these two carbon atoms, using these sp2 orbitals. But remember, there was also some p orbitals left over on each atom that weren't used, and this gives an opportunity for a second bond to form. So that would be the pi bond. A pi bond is formed by sideways overlap of p orbitals above and below the internuclear axis, the axis where the sigma bond occurs. So the pi bond has two regions where the orbitals overlap, recalling from the original diagram on the left that there's an upper lobe and a lower lobe. And so the electrons in the second bond, the pi bond, are going to occur both above and below the sigma bond, above and below the internuclear axis, as shown in this diagram. So the green portion is the sigma bond between the sp2 hybridized orbitals, and the second bond is a pi bond using p orbitals. One more type of hybridization to discuss is when you combine a single s and a single p orbital together, and you get two, again, equivalent hybrid orbitals that are called sp, and in this case they're going to have geometry that orients them 180 degrees apart. And so when that is the case, as shown on the right, there are two unhybridized p orbitals and the remaining parts of their atomic orbitals, and so you have some 90-degree angles amongst those as well. So what happens if you use those in making bonds between atoms? Well, here's another example of this type of hybridization between carbon atoms. Between carbon atoms on the left that have an sp orbital, sp hybrid orbital, and a p orbital that's in the vertical orientation, and a second p orbital on each of them on a different axis. I can't say for sure which one it is in that diagram, presumably the one going in and out of the plane of the diagram. And so if the two sp orbitals are used to make an internuclear bond, we call that the sigma bond, head-on overlap of those sp orbitals. Now there are two mutually perpendicular pi bonds formed by the overlap of the remaining p orbitals that were not used in making the sigma bond. And so that gives you a total of 3 bonds. So the sigma bond in this case is the first bond, and then there are 2 pi bonds for a total of 3 in this particular compound. So it's a carbon-carbon triple bond is going to include an sp hybrid and two sp hybrid in the sigma bond, and 2 p orbital overlapping in pi bonds. So the bottom line, what you really want to remember here is there's 3 types of hybrids, and they go very directly with the specific charge cloud arrangements that have been described previously in our conversation about VSEPR. Every time you have 2 charge clouds and linear geometry, it is sp hybridization. Be careful how I said that. Every time you have 3 charge clouds where there's trigonal planar geometry, it's going to be sp2 hybridization. And when there's 4 charge clouds, it's going to be tetrahedral geometry, the 109-degree kinds of angles, and sp3 hybridization. Simple as that. And when there's sp3, there's no leftover orbitals to use for multiple bonds. With sp2, there will be extra bonds, and sp also have extra orbitals left over for the formation of multiple bonds. Recall in the connection of this diagram from earlier in the chapter where each of these comes in. So the sp hybrids are going to be whenever you have linear molecules such as carbon dioxide. The sp2 molecule hybridizations will occur when you have trigonal planar electron geometry, whether it's with or without lone pairs. Either when, you'll still have sp2 hybrids. And then when there's 4 charge clouds in tetrahedral electron geometry, this will give you sp3. Be using sp3 hybrid orbitals whether you have 0, 1, or 2 lone pairs. The hybridization will still be including sp3. Now, just to give you a little more discussion on this and a couple of examples that might make this feel helpful to you. Okay, here's a compound called acetic acid. It's the primary component of vinegar in a dilute solution. And the geometry about carbon 1 is described as being tetrahedral. So that's this one here. Carbon 2 in the middle is trigonal planar. And oxygen 1 on the right is bent. And when given the information described so far, what would be the hybridization of the orbitals around C1, C2, and oxygen 1? All right, so carbon 1 is tetrahedral. Every time you have tetrahedral, There is nothing else to know. It's very straightforward. It's always going to be sp3 hybridization. So three of these choices have that. If you have trigonal planar for carbon 2, that has to be sp2. So these two choices here also have that correct value, but this is something else. We are not even going to discuss hybrids that include d orbitals. That's for someone else's course, not ours. And so if the oxygen atom is bent, we have to figure out what makes sense about that, because bent can come from one of two things. It's either going to be from 3 charge clouds or from 4 charge clouds. Well, oxygen has 2 bonds in this diagram, but in order for it to have an octet, and as is typical, oxygen is normally going to have, very often going to have 2 lone pairs. When that's the case, that would be 4 charge clouds, and that gives you sp3 as your hybridization for that atom. All right, now let's see if we remember what we saw in another picture. If you see a set of hybrid orbitals represented, and in this diagram they have 180 degrees between them, and there's 2 going in opposite directions, there's only one possibility that should make any sense. Given that angle, bond angle, it should be sp hybrids. Nothing else. All you need to know. 180 degree angles are always going to be sp hybrid orbitals, remembering that leaves unused 2p orbitals for possibility of making triple bonds. Here we have another molecule called urea. Urea has some nitrogens, hydrogens, carbon, and oxygen, and we need to determine what type of hybridization is expected for the carbon atom and nitrogen in urea, according to VSEPR. In order to make sense of this, we need to determine also how many lone pairs are present and necessary for the complete description of what each of these atoms contains. Okay, let's start with oxygen. Oxygen is red, it's on the right, and if it's shown with 2 bonds, that's 2 bonds there. That means that it doesn't have an octet unless you've got a 2 sets of lone pairs, 2 lone pairs on that oxygen. And the nitrogens, we need to have to think about them as well. The nitrogens are shown with 3 bonds, but unless you have some lone pairs on them, there would not be an octet. So each of those nitrogens should have a lone pair. And all right, so let's look at this. The carbon has 3 things attached to it. And so 1, 2, 3 charge clouds. So every time you have 3 charge clouds, the hybridization is going to be sp2. Well, nitrogen in each of these examples has also got 3 things attached. So 3 electron charge clouds, 1, 2, 3 on each of them. And so also for nitrogen, it's going to be sp2 as the hybridization for the nitrogens. Both of them have 3 charge clouds. Oh, they don't either. They have 4 because we forgot our lone pair. So it should be sp3 because there's the 4th one in the lone pair. Don't overlook the lone pairs as your 4th charge cloud. Now, what would the approximate values be for expected bond angles? All right, for the carbon, if it's sp2 and it's got 3 charge clouds around it, it better be close to 120 degree angles. And the nitrogen with sp3, we should expect should be the tetrahedral bond angle, and that's going to be essentially 109. It could be a little distorted because of lone pairs, but we won't stress over the fine-tuning of that actual value. And yet, in this diagram, we don't quite see angles like that exactly for the nitrogen. And so what are the actual hybridizations suggested based on the model shown? Well, from what this model looks like, I would suggest, and that's what threw me off to begin with when I was describing it for you, talking my way through the example, is that that lone pair of electrons on here was overlooked for a minute because this angle looks like the nitrogen should have a 120 degree angle. It looks flat, it looks trigonal planar. And so the actual hybridization that corresponds to that would then be sp2 instead. The carbon looks like planar, trigonal planar in my estimation. And so I would agree that this carbon should still also be 120 degree angles and sp2 hybridizations. A little bit of an interesting example. All right, one more molecule for an example to help you use these concepts of hybrid orbitals. All right, this is a molecule, it's an amino acid called glycine. And let's see what we can understand from just this skeletal diagram. We can determine where the molecule should have lone pairs and multiple bonds. Thinking in terms of octets. With these atoms, we don't have to go beyond octets. So if you start with the nitrogen on the left, it has 3 bonds, and that means that it better have something else, and that's very typical for nitrogen to have a lone pair. Hydrogen only gets 1 bond, so all the hydrogens look like they are appropriately situated. The carbon in the center has 4 bonds, no problem. The carbon to the right of center has 3 bonds. Oh, and so it doesn't have its octet yet. Do you add a lone pair? Not in this case, because the oxygen above it has 1 bond and the oxygen to the right has 2. Well, if oxygen to the right has 2 bonds, that's typical. Assuming you add 2 lone pairs, that oxygen will be exhibiting an octet. But if you put in a multiple bond between the carbon and the top oxygen, if you add lone pairs to that oxygen, now you have an octet for oxygen and for carbon. If you went back and counted up all the valence electrons for the atoms combining in this structure, this would be a reasonable Lewis structure for it. Okay, so having done that, what are the predicted approximate bond angles for these different locations for the carbon, hydrogen, carbon, hydrogen in the center of the molecule, and the oxygen with carbon and nitrogens? Well, the CHC in the middle is right here. It's got 4 bond electron clouds around the carbon, and so the bond angle is going to be that which we always have for 4 charge clouds, namely essentially 109 degrees, well, plus a little bit. And the second one is for the oxygen, carbon, oxygen angle down here, well, on the right side. So if you have 3 charge clouds around that carbon, so 3 charge clouds, electron charge cloud or groups, that would give us 120 degree angles expected around that carbon atom on the right. And then the nitrogen. Well, the nitrogen, what's on there? Well, it looks like 3 bonds and 1 lone pair. That's 4 charge clouds. And so for electron charge groups, clouds, whatever you want to say, same idea. That gives us the typical 109 degree tetrahedral geometry angle. Even if it's got a lone pair, it's going to be somewhere near that. Yes, there will be some distortion because of the lone pair. Again, not a huge consideration for our concerns here. So what if you have that much information? Which hybrid orbitals correspond to these carbons? Well, when you have 109 degrees with 4 charge clouds for the first carbon, that should be sp3. And when you have the second carbon has 3 charge clouds and 120 degree angles, that should be sp2. And the nitrogen has 190 degree angles. That would again be tetrahedral geometry and 4 electron charge clouds resulting from 3p orbitals and 1 s orbitals, making a set of 4 equivalent orbitals in tetrahedral geometry. We call that sp3. All right, try not to make this any more complicated than necessary. Please ask more questions if you need more clarification. Work as many examples as you can. Good luck studying, and see you in class.